last year, spring term and first question. It is an easy and mid-level question. There is no trick in the question. It is in Turkish here, and there are some solutions already published in my webpage. Here is the English version. So let's read and take notes. Understand first and then solve the questions. 102 kilowatts, 3-phase, 400 volts, 50 Hz, 2-pole, delta connected round rotor synchronous motor. Okay, let's take notes. We have a synchronous motor or synchronous machine operated as a motor. Okay, having some ratings. Mechanical output power, that is the rated power, 102 kilowatts. I write down it watts, not to be confused. Since it is given in 3-phase, always line-to-line voltages are given in 3-phase systems. So line-to-line voltage is 400 volts, 50 Hertz, and 2-pole. 2-pole means there is only one pair of pole, and round rotor. Round rotor or cylindrical rotor machine is under observation. Has a negligible amount of armature resistance. RA is 0, and the machine has got 1 ohm of synchronous reactance. XS is equal to 1 ohm. Okay. Mechanical losses are given as 2500 watts. Mechanical losses are given as 2500 watts. Those are total mechanical losses in terms of frictional and windage losses, and they are constant. You know, mechanical losses are function of speed. Since machine is operated as synchronous speed, which is constant, there is no change in mechanical losses. It is assumed constant. The machine is magnetically linear and there is no saturation. That is an extra information. Otherwise, there must be some curves given related with the saturation or showing the non-linear relation between the parameters. Okay, what is asked? What are the questions? Calculate the shaft torque. Calculate the shaft torque. Okay, now let's understand or repeat what we have read so far. Here's a synchronous motor having 3-phase. Was it star or delta? Delta connected. That is very important, you know, delta connected. It is very important. Since machine is delta connected, winding voltage or single phase voltage is equal to line voltages because it is delta connected. Okay, and it is 400 volts, and it is delta connected. The machine is operated on a network having 400 volts line-to-line voltages, having 50 Hertz, and here's a mechanical output. Its rated value is 102 kilowatts, I think. It was, yes, 102 kilowatts. Then that is the mechanical output. There must be some electrical input. Perhaps there would be some reactive exchange. We don't know yet. Here must be an excitation winding, applied some DC to convert energy. It is converting energy. It is producing mechanical output. So, what is the point? Calculate the shaft torque. Ta-ta! Torque. Torque is a parameter of shaft. And here's angular speed, you know, which is synchronous speed. What is the condition machine is operated? Let's read that again. For example, machine would be such a machine, but it would be operated at its half value. But there is no information about that. There is no information. In such a case, you can ask the lecturer, or there is no any other solution. The only choice is using rated output power. So it would be better to write down here what is the rated torque. Calculate the rated torque. Rated output is equal to rated torque times rated speed. Rated speed is angular speed, which is 2 pi ns over 60. Here's rated torque to be calculated. Here's the rated power. Rated torque is equal to 102 kilowatts or watts over 2 pi ns is equal to 60 F over pole pair number. Here is 50. 60 times 50 makes 3000. Here there is only one pair of pole. That means synchronous speed is 3000 RPM. So 2 pi 3000 over 60 is the angular speed. Let's calculate. Ns is equal to 60 times F over pole pair number. Synchronous speed is equal to 3000 RPM, and angular speed omega synchronous is equal to 2 pi ns over 60, and it is such a radians per second. And then rated mechanical output torque, shaft torque, is equal to rated mechanical output over angular speed of the shaft, which is rated value always, because machine always rotate at synchronous speed. As you see, 324 Newton meters. That is the rated torque generated on the shaft, produced on the shaft, or delivered to load. Here's a motor, here's the shaft, here is the mechanical load, and this guy delivering 102 kilowatts or watts mechanical output power, and here is some torque having a value of 324 Newton meters, something like that, and here's an angular speed, something like that. It was, as I remember, yes. Okay. We got to point. Load is consuming such a power. Motor is supplying such a power. System is in equilibrium, in balance, since there is no change in speed. Remember Newton's equation. Net torque is equal to J dW over dt, angular acceleration. Since there is no speed change, applied torque to load, which is mechanical output torque of motor, minus load torque must be 0. So motor shaft torque is equal to load demand. Those are equal in steady state. Okay. We have calculated the first question. We have just calculated shaft torque. Let's continue. Calculate the active power of motor drawn from the network. To answer this question, you should remember the power balance equation. You apply electric power. We always call P, not PE. Electric power. Here would be some copper losses in armature, and then rest of the power will be converted into mechanical power in armature. Then here would be some mechanical losses. Rest of the power will be net mechanical output. Mechanical output. Okay, ladies and gentlemen, here it is given 102 kilowatts. Mechanical losses were given to 2500 watts. So all those makes such a power in armature generated, induced, some of yes, and then there is no, armature resistance is negligibly small, so there is no copper losses in armature. This guy eliminated, so input power is equal to induced power. So let's write it again. Input power is equal to converted power, since there is no copper loss in armature, and then it is equal to mechanical losses plus shaft power. Okay, let's substitute the values here. P, electric power, is equal to PD, which is converted power. It is not known yet. PD is equal to mechanical losses, I have defined here, plus mechanical output, beep, plus mechanical output. At the right time, at the time, mechanical output is rated value, so converted power is such a value, and electric input power has the same value, watts. We have already calculated here. It was 104,500 watts. That's the input power. Beep beep. that power is drawn from the network here. 104 plus 500 watts. Yes, continue. We have solved the question B. Let's try on C. Calculate the line current of motor drawn from the network. In the question, here are 3 lines. Each line carry line current, and it is asked under these conditions. Do not forget, machine is connected delta. Here is 3-phase system having line-to-line voltages of 400 volts. So in brief, here is our motor, synchronous motor, delta connected, and then UVW, those are the terminals, and here is line current. Okay, what is line current? What is the power factor? Let's turn back the question. Calculate the line current of motor drawn from the network. There's something missed, I think, in English version. I have prepared this version just before the lecture today. Power factor cannot be seen here. Let's turn back to Turkish version. Yes, here's one sentence is missed. Okay, I am very sorry about that. Motor is operated at its rated output power and power factor is 0.8 leading. Okay, here is something missed, but I said motor is loaded at its rated value. Rated value is this. We have already considered in these questions, with a 0.8 leading power factor. Power factor is 0.8 leading. Do not confuse. Not lagging, leading. So here's a power factor 0.8 leading. Machine is driving full load or rated load, which is such an output power. There was some input power, electric power, 104,500 watts. Under these conditions, what is the line current? Now it looks easy. Power in 3-phase systems can be written in 2 different equations. Square root 3 times line voltage, line current, and power factor, or simply cosine phi, or 3 times single phase voltage, single phase current times power factor. If you use line parameters, you should use root 3. If you use single phase parameters, you should multiply the result by 3 times. Now it is easy to use line parameters here. This guy asked, so line current is electric input power over root 3 times line to line voltages and power factor. Now it is not important to consider whether it is lagging or leading here in this equation. It makes no change because the angles between these range always result in a positive power factor, positive cosine phi, since cosine function is an even function. Okay, so let's calculate this. Line current, in fact there were two more data given. Motor at rated load, that was the one of the given parameter, and power factor is 0.8, which is leading. That was the another issue we have missed here. We have added 0.8 leading power factor. Okay, let's continue. Power, electric power over square root of 3 times line to line voltage times power factor or cosine phi. Okay, you have calculated the current as beep, such a current 188. Let's check it. C 188. Okay, it's okay. Let's continue the D. Calculate the reactive power of the motor. Attention, take care. The sign or future, whether it is forward or backward or inductive or capacitive, those features must be correct, must be evaluated. Let's calculate reactive power. Reactive power is similarly can be written as square root times line to line voltage, line current, and sine phi coming from power factor. But the sine of the phi must be considered again. After you have making calculations, please consider the meaning of leading angle, leading power factor. What does it mean? Let's calculate reactive power and then consider the meaning. Reactive power similarly to this equation, square root 3 times voltage line to line times current line to line times sine phi. Houston, we don't know sine phi. We know phi is the angle having a value of arc cosinus power factor, which is 0.8. Houston, it is such a radians. such a radian, but it is difficult to interpret for me since it is radians. Let me convert it into degrees to make easy interpretation. It has got such a degree, which is leading, ladies and gentlemen, leading angle. We should consider this. Okay, let's continue. All those parameters right now are known. Sine delta is known because sine phi is known because we know the phi. My calculator only accepts radians, so I use this value here as a variable. So here you see such a reactive power, in terms of volt amps reactive. That is the unit of reactive power. Ladies and gentlemen, what about the property? Current was leading. The power, sign of power, whether it be positive or negative. Ladies and gentlemen, remember complex power equation in electric circuit theory. Voltage times current conjugate, complex conjugate. So it means if you have a positive phi, the result would be JQ, that's the complex power. A result would be a negative due to complex conjugate. If phase angle is positive, Houston, reactive power would be negative. If phase angle is negative, in such a case, reactive power is positive. There is something confusing due to passive sign convention. That is a convention. That's a passive power convention. So here is a complex conjugate. So you should consider the sign. You should evaluate the sign. The phase angle is leading, so reactive power must be negative, or the other words, must be leading reactive power. Leading current causes leading reactive power, and it is negative. Lagging current, which is negative phase difference, result in positive reactive power or lagging reactive power. Here is something confusing. That confusion comes from complex conjugate here. So let me make a little bit correction. Here must be minus due to complex conjugate. That is the reactive power, ladies and gentlemen. Minus 78 kilovolt ampere reactives. Okay. We have calculated reactive power. Let's check it out. Yes, here it is. Let's continue. E. Calculate EMF. Only RMS value is required, desired. You know, EMF has a magnitude and a phase angle with respect to reference. But here is only RMS value. Magnitude is desired. Okay. The first method you should choose or try is using Kirchhoff's voltage law around the equivalent circuit. Machine is operating as a motor, so let's draw the phasor diagram. Let's draw the equivalent circuit. Here is EF, induced EMF. Here is XS, synchronous reactance. Armature resistance is neglected, so I have skipped the resistance here. Here's the terminal voltage. And let's apply Kirchhoff's voltage law around this loop because current is incoming. We supply from the terminal. Here's the device making energy conversion. That is, let's apply Kirchhoff's voltage law around the loop. Applied terminal voltage is equal to summation of the voltages around the loop. Terminal voltage EF plus I1 XS J. Phasor. Please do not forget phasors and complex variables. And then our mission is to find out the RMS value of EMF. So EMF is equal to V1 minus J I1 XS, phasor. And to emphasize, here is an angle in polar form. That is the reference vector having zero phase displacement minus J I1. Here is the phase difference with respect to reference, which is phi, power angle, and here is XS, here is J. Ladies and gentlemen, that is magnitude, here is magnitude. So let's calculate this one because we need EF magnitude. But let's read the question again. Machine is connected delta, so the current here is winding current. Here's a machine, let's say here's a delta winding. Let's say here is a line current, I1 line, and here are single phase currents. Single phase current is smaller, so I1 line over root 3 is the winding current or single phase current that is valid for delta connection. In delta connection, you also know that applied terminal voltage, line to line voltage, is directly equal to single phase winding voltage. Again, it is valid for delta connection. Let's calculate this equation. Please take care because here are phasors. It is easy to make error. Okay, let's try V1. Yes, machine knows V1. It is equal to V1 line. It is already calculated here. Okay, what about current? I1 is unknown, so let's calculate I1 line over root 3. Excuse me, there's a mistake. Root 3, and it is such a value since it is connected delta. Current can be written as like this because it is connected delta. Now our aim is to construct this equation. Okay, do it. Induced EMF is equal to V1 plus or minus J times I1 times XS, and calculator says that J is not defined. It is a complex parameter having a value of square root of -1. But Houston, you know I1 is 108. What about phase angle? Phase angle is leading positive angle, but you should make these element a phasor. Houston, you should make it phasor. How can you manage this? There are two possibilities. You can write I1 phasor, I1 magnitude times cosine phi plus j sine phi. That is the Cartesian equation. The other one can be written as I1 times e to the j phi. It is easier in MathCAD, so let's try it. I1 is here. It is already magnitude times e to the j phi. As you see, now it is a complex parameter, and the angle looks positive. Phi is positive. You already know it is positive, 36, 37 degrees. Houston, you should substitute current here as phasors. Okay, I have substituted. V1, it is reference. V1 is reference. I mean the angle is 0, so there is no imaginary part. It looks like A times J0. No imaginary parts, so it is already real part, no problem. XS is here, J is here, so EMF is a complex number having a negative angle, as you see, and the angle of EMF can also be written as delta. Delta is, you know, torque angle or load angle. It is argument of EF. Such a radian. Houston, it is negative. Yes, it is negative because machine is operated as a motor. In motor it is negative, so it was radians. So let's convert it into degrees. That is degrees. That is radians. Houston. And now what you see, in fact in the question E, only RMS magnitude. So only RMS magnitude, which is the absolute value of EF. It is RMS magnitude such a volts. Okay, we got it. Amplitude of EMF is 473 blah blah volts. The next question, calculate the load angle in degrees. Take care the sign of delta, load angle must be correct. In fact, we have already calculated a few minutes ago. Delta was 10.6 degrees and it was negative. It was negative, remember? It was negative, lagging, because it is operated as motor. Let's check it out again. Here it is, minus 10.6 degrees. We have already done this. Okay, let's calculate the final question. Calculate the inner power angle, which is psi, in degrees. Attention, the sign of psi must be correct. What is psi? Houston, remember, psi was the inner power angle. It's a special angle. That is the angle between EF and I1 phasors. Please remember the similarities. Power at a terminal can be written as 3 times voltage of terminal, current at the terminal single phase, and then cosine phi. Here's phi is the angle between voltage and current phasors. Here are dot products. The element, here's the equivalent circuit. Inner power or induced power, PD, induced converted on these elements, can easily be written as PD 3 times voltage, current, and a cosine of angle between those two vectors, which is psi. Psi is the angle from EF to current. That is dot product. Remember, dot product you should multiply by cosine. Okay, you have remembered this. The question asks what the inner power angle is. What the inner power angle is. The easy method to find out its value and sign is drawing phasor diagram. Remember motor's equation. EF is equal to V1 minus JI1 XS. That is the motor's equation. Okay, that is the V1, which is 400 volts now. And then here's a leading current. Here was a leading current. Let me find it out. Current I1 108.8. Here's the leading current I1, possibly 37 degrees approximately. I1 is 108, was it? Yes, amps. And then subtract this guy to subtract the perpendicular J I1 XS. That is the perpendicular relation. For the subtraction, you should substitute this guy here, J I1 XS. Finally, you got EF, which is 473. It was, yes, 473 volts. And Houston, that is phi, that is delta. As you see, it is negative. Delta phi is positive leading current. Delta is negative motor operation. So the question is, what is the psi from EF to current? That is psi from EF to current. Okay, psi is negative of delta plus phi from the interpretation of phasor diagram. Please do not memorize, just draw and calculate or interpret. Let's do it. Psi is minus delta plus phi. That is such a radian. It looks positive, and let me convert it into degrees. 180 over pi is the conversion coefficient, so it is 47 degrees, which is leading. Here you see current is leading. That is the counterclockwise rotation, which is positive rotation. You start from voltage, move in positive rotation direction to find out current, and it is positive. Psi is 47 degrees positive, I mean leading current. That's the end of the question.